What if I told you that the chair you're sitting on, the phone in your hand, maybe even your own body, doesn't actually exist when you're not looking at it? Not in some philosophical, tree falling in the forest way. I mean literally, physically, according to the most well-tested theory in all of science. The atoms that make up everything around you exist in a ghost-like state of infinite possibility until the moment something interacts with them. And here's the part that will absolutely shatter your understanding of reality. The evidence for this is so overwhelming, so repeatedly verified, that denying it would be like denying gravity. Right now, as you watch this video, you are not observing a pre-existing reality. You are collapsing infinite possibilities into the single reality you experience. Every glance, every touch, every measurement you make is literally creating the definite world around you from a sea of quantum maybes. This isn't philosophy. This is physics. And by the end of this video, you'll understand why some of the greatest minds in science believe that matter, in its most fundamental form, only truly exists in the act of interaction. Before we dive into what might be the most mind-bending journey you've ever taken, do me a favor. Hit that like button and subscribe, because you're going to want to revisit this video multiple times to fully grasp what we're about to explore. Also, drop a comment telling me what country you're watching from and what time it is where you are. I'm genuinely curious about our global community, exploring the nature of reality together. Let's start with something that seems simple. What is matter? For most of human history, we thought we knew. Matter is stuff. Solid, tangible, real stuff that exists whether anyone's looking at it or not. Your ancient ancestors would have laughed at the question. Of course, the rock exists when you're not looking at it. Of course, the tree is still there when you walk away. Then in 1900, a German physicist named Max Planck discovered something that would begin unraveling everything we thought we knew about reality. He wasn't trying to revolutionize physics. He was just trying to solve a boring problem about how hot objects radiate light. But his solution required something weird. Energy could only be emitted in discrete packets, which he called quanta. Think of it like this. Imagine you thought water could flow in any amount, and then you discovered that water only comes in droplets of specific sizes. No matter how you pour it, it's always exact multiples of one fundamental drop. That's what Planck discovered about energy. Reality isn't smooth and continuous. It's granular at the smallest scales. But here's where it gets interesting. In 1905, a young Albert Einstein took Planck's idea further. He proposed that light itself isn't a wave that exists everywhere at once, but rather a stream of discrete particles he called photons. But wait, scientists had already proven light was a wave through countless experiments. How could it be both? This was the beginning of the quantum nightmare that would haunt physics for the next century. Fast forward to 1925. A brilliant young physicist named Werner Heisenberg is struggling with this wave-particle duality. He's trying to track the position and momentum of electrons, and he keeps hitting a wall. No matter how precise his mathematics, he can't pin down both properties simultaneously. And then he has a revelation that changes everything. What if it's not a limitation of our measuring tools? What if the electron simply doesn't have a definite position and momentum at the same time? What if, at the quantum level, reality itself is fundamentally uncertain? This became the Heisenberg uncertainty principle, and it's not about our ignorance. It's about reality itself. The electron doesn't have a definite position until something measures it. Before that moment, it exists in what we call a superposition, a ghost-like state of all possible positions at once. Now, I know what you're thinking. Okay, but that's just tiny particles. That doesn't affect the real world, right? Wrong. Dead wrong. And here's where your understanding of reality is about to take its first major hit. Let me describe to you the most disturbing experiment in all of science. It's called the double-slit experiment, and it was first performed by Thomas Young in 1801, long before anyone knew about quantum mechanics. Here's the setup. You take a barrier with two thin slits in it. You shoot particles, like photons or electrons, at this barrier. Behind it, you have a detector screen that shows where the particles land. Simple question: what pattern do you expect to see? If particles are like little bullets, you'd expect two bright bands on the screen, corresponding to the two slits. Some particles go through slit A, some through slit B, and you get two clusters. But that's not what happens. Instead, you get an interference pattern, multiple bands of light and dark, exactly like what you'd see if waves were passing through the slits and interfering with each other. The particles are somehow acting like waves, going through both slits simultaneously and interfering with themselves. Okay, weird, but maybe particles are just waves, right? Here's where it gets absolutely insane. Scientists decided to detect which slit each particle actually goes through. They set up detectors at the slits to watch the particle's path. And the moment they did that, the interference pattern disappeared. The instant you observe which slit the particle goes through, it stops acting like a wave and starts acting like a particle. It's as if the particle knows it's being watched and changes its behavior accordingly. But wait, it gets even more disturbing. In 1978, physicist John Wheeler proposed a delayed choice variation of this experiment. What if you decide whether to measure which slit the particle went through only after it's already passed the slits? The experiment was performed, and the results were shocking. The particle's behavior in the past seems to depend on what measurement you choose to make in the future. Decide to measure which slit, and the particle retroactively goes through one slit. Don't measure, and it retroactively went through both. Think of it like this. Imagine you're walking through a doorway in your house. Later, someone sets up a camera to check which side of the doorway you walked through. And depending on whether they check the camera or not, you retroactively either walked through the left side, the right side, or somehow both sides at once. That's not just weird. That's reality-destroying weird. What this experiment tells us is profound. The particle doesn't have a definite path until something measures it. Before observation, it exists in a superposition of all possible paths. The active interaction of measurement is what collapses this superposition into a single reality. Matter doesn't just exist in some predetermined state waiting to be discovered. Matter exists in a haze of possibilities, and only through interaction does it become definite. Here's your first mind-blown moment. The history of a particle is not determined until it's measured. The past itself is, in some sense, created by present interactions. Now let's take this weirdness and multiply it by a factor that will make your brain hurt. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper trying to prove that quantum mechanics must be incomplete. They couldn't accept that reality was as weird as quantum mechanics suggested. They proposed a thought experiment, now called the EPR paradox, involving what we now call quantum entanglement. Here's how entanglement works. When two particles interact in certain ways, they become correlated, not just connected, but fundamentally, irreversibly linked at the quantum level. Once entangled, these particles share a quantum state. If you measure one particle and find it spinning clockwise, the other particle, no matter how far away, will instantly spin counterclockwise. Einstein hated this. He called it Spökkraftverwirkung, spooky action at a distance. He thought it proved quantum mechanics was incomplete because nothing should be able to influence anything else faster than light. There must be hidden variables, predetermined properties that we just don't know about yet. For decades, this was just a philosophical debate. Then in 1964, Irish physicist John Stuart Bell developed a mathematical theorem that could actually test whether hidden variables existed. He created what's now called Bell's inequality, a statistical test that would give different results depending on whether particles had predetermined properties or genuinely existed in superposition until measured. In 1972, Physicists John Clauser and Stuart Friedman performed the first real test. Then in 1982, French physicist Alain Aspect performed even more rigorous experiments. The results? Bell's inequality was violated, dramatically, repeatedly, in every single experiment. Hidden variables don't exist. The particles genuinely don't have defined properties until they're measured. And when you measure one entangled particle, the other responds instantly, no matter the distance. Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize in Physics in 2022 for proving this beyond any shadow of doubt. Experiments have now entangled particles across distances of over 1,200 kilometers. The speed of the correlation has been tested to be at least 10,000 times the speed of light, and possibly truly instantaneous. Think of it like this. Imagine you have two magic coins. You flip one in New York, and it comes up heads. At that exact instant, without any signal passing between them, the other coin in Tokyo instantly becomes tails. Not because the result was predetermined, but because the coins share a single quantum state that only becomes definite when one is measured. Here's the truly mind-bending part. Before you flip the first coin, both coins are neither heads nor tails. They exist in a superposition of both. The act of flipping one coin creates the definite result for both coins simultaneously, regardless of distance. This tells us something profound about interaction. When particles interact to become entangled, they form a system that cannot be described separately. They become a single entity spread across space. The interaction has created a new kind of existence that transcends individual particles. Matter doesn't just exist in isolation. The very concept of separate, independent objects breaks down at the quantum level. Everything that has ever interacted remains connected in ways we're only beginning to understand. 39 minutes and 0 seconds to 51 minutes and 0 seconds. Wave function collapse the moment reality crystallizes, so we know particles exist in superposition. We know they're connected through entanglement. But what exactly happens in the moment of interaction that transforms possibility into reality? This is where we encounter one of the deepest mysteries in physics: wave function collapse. In quantum mechanics, every particle is described by a wave function, a mathematical object that encodes all possible states the particle could be in. This wave function, usually denoted by the Greek letter psi, evolves smoothly and predictably according to the Schrödinger equation, developed by Austrian physicist Erwin Schrödinger in 1926. When nothing is interacting with the particle, its wave function spreads out, encompassing more and more possible positions, states, and properties. The particle is everywhere and nowhere, spinning in all directions at once, moving at all speeds simultaneously. Then, the moment something measures or interacts with it, the wave function instantaneously collapses. All those infinite possibilities vanish, and the particle snaps into one definite state. But here's the question that has haunted physics for a century. What counts as an interaction? What causes the collapse? Is it conscious observation? Does it require a human mind? Or does any physical interaction, even between two atoms, count? Different physicists have wildly different answers, and this disagreement has spawned competing interpretations of quantum mechanics, each more bizarre than the last. The Copenhagen interpretation, championed by Niels Bohr, says that the wave function represents our knowledge of the system, and collapse happens when we gain information through measurement. But this seems to give a special role to observers, which feels uncomfortable. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function never collapses. Instead, every possible outcome occurs, but in separate, parallel universes that split off at each quantum event. You're not collapsing possibilities. You're becoming one version of yourself in one branch of an infinitely splitting multiverse. The objective collapse theories say that wave functions spontaneously collapse without observation, triggered by factors like gravity or reaching a certain size threshold. This was proposed by Italian physicists Ghirardi, Rimini, and Weber in 1986. The relational interpretation, developed by Carlo Rovelli, says that quantum states are not absolute, but relative to the observer. The particle may have a definite state relative to you, but remain in superposition relative to something else. Properties are not intrinsic, but relational. Here's what all these interpretations agree on. Interaction changes everything. Whether it collapses the wave function, splits the universe, or establishes a relation, the moment two quantum systems interact is the moment when definite properties emerge. Think of it like this. Imagine reality as a fog of infinite possibilities. Interactions are like flashlights cutting through the fog. Each being creates a path of clarity, of definiteness, through the haze. But the fog is still there in every direction the light doesn't reach. Before interaction, asking where is the particle is like asking what shape is the fog. The question doesn't make sense. The particle doesn't have a location in the way we normally think about it. Only through interaction does where become meaningful. Only through interaction does the particle gain definite properties. Only through interaction does matter, as we understand it, exist. Okay, but if particles exist in superposition until measured, why don't we see this in everyday life? Why doesn't your chair exist in multiple places at once? Why does the macroscopic world seem so solid, so definite, so classical? This puzzled physicists for decades. The answer came in the 1970s and 1980s through the work of physicists like Wojciech Zurek, who developed the theory of quantum decoherence. Here's the key insight. In the real world, nothing is truly isolated. Every particle, every atom, every molecule is constantly bombarded by photons, air molecules, and electromagnetic fields. Each of these interactions is a measurement. When a single particle is in superposition, it maintains what's called quantum coherence. All its possible states are connected, able to interfere with each other like waves. But the moment it interacts with its environment, those states begin to decohere. The connections between possibilities break down. The particle becomes entangled with countless environmental particles, spreading its quantum weirdness across too many systems to ever bring back together. Think of it like this. Imagine you're whispering a secret to one person. Easy to keep secret. Now imagine you whisper it to 10 people, who each whisper to 10 more, who each whisper to 10 more. Within minutes, your secret has spread to thousands, getting distorted and mixed with other information. You could never gather everyone back together to reconstruct the original secret perfectly. That's decoherence. The quantum information doesn't disappear. It just becomes so spread out, so entangled with the environment, that it's functionally irretrievable. For something the size of an atom in room temperature air, decoherence happens in less than a trillionth of a second. For something the size of a dust particle, it's nearly instantaneous. For something the size of a chair, it happens so fast that quantum superposition never gets a chance to manifest. This is why your chair seems solid and definite. It's not that the quantum rules don't apply to it. It's that the chair is interacting with so many things simultaneously, so constantly, that it's being measured into definiteness quintillions of times per second. But here's the fascinating part. Decoherence doesn't actually solve the measurement problem. It explains why we don't see superpositions in everyday life, but it doesn't explain what happens in the fundamental moment of interaction. It just pushes the question deeper. What happens when that first photon hits an atom? What transforms possibility into reality? Some physicists argue that decoherence is all you need, that once quantum information has spread sufficiently into the environment, the system effectively has definite properties. Others argue that something more is needed, some actual collapse mechanism. What we can say with certainty is this: interaction with the environment is what creates the appearance of classical reality. The definite, solid world we experience emerges from constant, relentless quantum interactions happening at scales we can't perceive. Matter exists in a perpetual state of interaction. The reason the chair seems to exist continuously is not because it has some intrinsic, independent existence. It's because it's continuously interacting with light, air, heat, and countless other things. Remove all those interactions, and the quantum weirdness would return. Now let's go even deeper. Everything I've told you so far treats particles as fundamental things that happen to interact. But modern physics suggests something far stranger. Particles aren't fundamental at all. Interactions are. Welcome to quantum field theory, the framework that combines quantum mechanics with special relativity and describes all known particles and forces except gravity. In quantum field theory, developed primarily in the 1940s and 1950s by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, particles are not little billiard balls. They're not even waves in the traditional sense. They're excitations in quantum fields that permeate all of space. Think of it like this. Imagine the entire universe is filled with an invisible ocean. Particles are ripples, waves, or vibrations in this ocean. An electron is not a thing traveling through space. It's a localized excitation in the electron field. A photon is a vibration in the electromagnetic field. But here's where it connects to our question about interaction. These field excitations only become real, only manifest as particles we can detect through interactions with other fields. The electron field and the electromagnetic field are constantly interacting. When an electron absorbs a photon, what's really happening is that the electron field and the electromagnetic field are coupling, exchanging energy, transforming into each other. The electron doesn't exist independently and then interact. The interaction is what creates the reality of both the electron and the photon in that moment. In fact, quantum field theory describes all of physics as fields interacting with fields. The standard model of particle physics, our most successful theory ever, is essentially a description of how different quantum fields couple to each other. Every particle you've ever heard of, every force, every phenomenon comes down to fields interacting. And these interactions aren't secondary to the existence of the fields. In a deep sense, the interactions define the fields. Physicist Carlo Rovelli puts it beautifully. The world is not made of fields. The world is made of quantum events. Reality is a network of interactions. Here's where your mind should be exploding. Matter isn't stuff that interacts. Matter is patterns of interaction in quantum fields. The electron in your body doesn't exist as a persistent object bouncing around. It's a recurring pattern of field interaction, continuously recreating itself through quantum processes. You are not made of matter that exists independently and happens to interact. You are made of interactions. Your atoms, your molecules, your cells are all patterns of quantum field interactions, sustained by continuous coupling with other fields. Without interaction, the very concept of particles becomes meaningless. The fields would still be there, but nothing definite, nothing we could call matter, would exist. Let's take this even further with one of the most radical interpretations of quantum mechanics. Relational quantum mechanics, developed by Italian physicist Carlo Rovelli in the 1990s. Rovelli asks a simple, a profound question. If quantum mechanics tells us that properties only become definite through interaction, why do we keep assuming that there's something underlying with intrinsic properties waiting to be revealed? What if there are no intrinsic properties? What if everything, literally everything, exists only in relation to something else? In relational quantum mechanics, a particle doesn't have a position, or a momentum, or a spin. It has a position relative to you, a momentum relative to another particle, a spin relative to a measuring device. Properties are not features of objects. They're features of interactions between objects. Think of it like this. Imagine asking, is a person tall? The question doesn't make sense without context. Tall, compared to what? Relative to a child? Yes. Relative to a mountain? No. Height is a relational property, not an intrinsic one. Now imagine that every property works this way. Not just comparative properties like height, but fundamental properties like position, velocity, even existence itself. An electron has a definite position relative to the detector that measures it, but relative to another electron that hasn't interacted with it, the first electron remains in superposition. Both descriptions are simultaneously true. Quantum states are not absolute. They're observer-dependent. This isn't just philosophical speculation. It's mathematically rigorous and resolves many paradoxes in quantum mechanics. Remember Schrodinger's cat, the famous thought experiment where a cat in a box is both alive and dead until observed? Relational quantum mechanics says the cat is alive and dead relative to us outside the box, but the cat itself, having interacted with the quantum decay event, is in a definite state relative to itself. The paradox disappears once you realize that quantum states are relational, not absolute. What this means for our question about matter is profound. Matter doesn't exist in any absolute sense. An atom exists relative to the atoms it interacts with, relative to the photons that bounce off it, relative to the measuring devices that detect it. But there's no perspective-independent answer to what state is this atom in. The universe doesn't have a view from nowhere, a God's eye perspective from which everything has definite properties. Reality is thoroughly relational, a vast network of interactions, each creating definite properties relative to itself. You don't observe a pre-existing reality. You interact with the universe, and in that interaction, both you and what you interact with gain definite properties relative to each other. Before the interaction, asking, "What is its state?" is like asking, "What is one hand clapping?" The question presupposes something that doesn't exist. Here's your second major mind-blown moment. You don't exist in any absolute sense. You exist relative to the things you interact with. Your definite, concrete experience is the view from inside a web of interactions that define you into being. Now we need to talk about the most fundamental interactions of all, space and time themselves. Everything we've discussed so far assumes that space and time are a fixed stage on which quantum events play out. But Einstein's general relativity, confirmed by countless experiments since 1915, tells us that space and time are not fixed. They're dynamic, flexible, warped by matter and energy. The problem is that general relativity and quantum mechanics don't play nicely together. General relativity treats space-time as smooth and continuous. Quantum mechanics says everything is discrete and probabilistic. Combining them has been the holy grail of physics for nearly a century. One promising approach is loop quantum gravity, pioneered by Carlo Rovelli, Lee Smolin, and Abhai Ashtekar in the 1980s and 1990s. It suggests that spacetime itself is quantized, made of discrete loops or networks at the Planck scale, about y-35 meters. In this view, spacetime is not a thing. It's a relationship. Space emerges from the interaction of quantum events. Time is not a river flowing independently. It's the order in which interactions occur. Think of it like this. Imagine you're trying to describe where cities are located. You might think you need a pre-existing map, a fixed space, to place them in. But you could also describe locations purely relationally. New York is 200 miles from Boston, which is 1,000 miles from Chicago, which is 2,000 miles from Los Angeles. You've described spatial relations without assuming space exists independently. Loop quantum gravity suggests reality works like this at the fundamental level. Space is the network of relationships between quantum events. Time is the sequence of interactions. Another approach, string theory, suggests that fundamental entities are not particles, but tiny vibrating strings. Different vibrations create different particles. But crucially, these strings don't exist in space. Space emerges from the interactions between strings. What both approaches suggest is stunning. Space and time are not the containers in which interactions happen. Space and time are what interactions create. The stage is not separate from the actors. The actors create the stage through their performance. Recent work in quantum gravity, particularly in an approach called causal set theory, suggests that space-time is built from discrete events and the causal relationships between them. An event only has location and time relative to other events it's causally connected to. What does this mean? It means that at the deepest level, interaction isn't just fundamental, it's the only thing. Everything else, including the arena of space and time in which we think interactions occur, emerges from interaction itself. Matter doesn't exist in space and time, interacting occasionally. Interaction creates space, creates time, and creates matter all at once. Now we need to address the elephant in the room. What role does consciousness play in all this? When we say observation collapses the wave function, do we mean a conscious observer? Is human awareness special? Or does any interaction, even between unconscious particles, count as observation? This question has spawned more mysticism, misunderstanding, and pseudoscience than perhaps any other in physics. Let's clear it up. In the early days of quantum mechanics, some physicists, including Eugene Wigner, suggested that consciousness might play a fundamental role in collapsing wave functions. Wigner even proposed a thought experiment, Wigner's friend, exploring whether consciousness was necessary for collapse. But modern physics has largely abandoned this view. The key realization came from understanding decoherence. Any interaction that transfers information, that entangles systems, functions as a measurement. No consciousness required. When a photon bounces off an electron, the photon carries away information about the electron's position. That's a measurement, even if no conscious being ever sees the photon. The electron's wave function has effectively collapsed relative to that photon. Physicist Wojciech Zurek showed mathematically that interaction with the environment is sufficient to explain the appearance of wave function collapse. You don't need consciousness. You just need interaction. Think of it like this. Imagine you walk through snow, leaving footprints. The snow has now measured your path. It contains information about where you walked. No consciousness was needed for this measurement to occur. But here's where it gets subtle. While consciousness isn't necessary for measurement, observers are still special in quantum mechanics. Not because we're conscious, but because we're large, complex systems that have many interactions with our environment. When you look at a particle, you're not collapsing its wave function with your mind. You're entangling its quantum state with the quantum states of trillions of atoms in your retina, which connect to neurons, which create cascading electrochemical signals throughout your brain. You're not outside the system, magically causing collapse. You're part of the vast web of interactions. The definiteness you experience is the definiteness that emerges from your perspective within this web. So consciousness doesn't create reality in some mystical sense, but your interactions, which happen to give rise to conscious experience, do participate in creating the definite reality you perceive. Here's a crucial point. The question, does matter exist when no one observes it, is a bit of a trick question. It assumes consciousness is special. The better question is, does matter have definite properties when it's not interacting with anything? And the answer to that is unambiguously no. Not because consciousness is magic, but because interaction is how definite properties come into being. Consciousness is irrelevant. Interaction is everything. You might think quantum effects are only relevant at atomic scales, but recent discoveries in quantum biology reveal that life itself exploits quantum interactions in surprising ways. In 2007, researchers at UC Berkeley discovered that photosynthesis, the process plants use to convert light into energy, relies on quantum coherence. When a photon hits a chlorophyll molecule, the energy doesn't travel along a single path to the reaction center. It exists in a superposition of all possible paths, exploring them simultaneously, and finds the most efficient route. This quantum effect persists for hundreds of femtoseconds, far longer than scientists thought possible in the warm, wet environment of a living cell. The plant is essentially using quantum superposition to maximize energy efficiency. Think of it like this. Imagine you're trying to navigate a maze. Classically, you'd have to try one path, backtrack, try another until you find the exit. But with quantum superposition, you could explore all paths simultaneously and instantly know the best one. That's what happens in photosynthesis. The energy exists in multiple places at once until it finds the optimal path and collapses into that reality. Birds might use quantum entanglement for navigation. Research by Peter Hoare and others suggests that European robins have molecules in their eyes where pairs of electrons become entangled. The Earth's magnetic field affects these entangled states differently depending on the bird's orientation, possibly allowing them to see the magnetic field. Our sense of smell might work through quantum effects. Luca Turin proposed that we distinguish scents not just by molecular shape, but by the quantum vibrations of molecules. When a smell molecule binds to a receptor in your nose, an electron might quantum tunnel through the molecule, detecting its vibrational frequency. Even more speculative, but fascinating. Some researchers, like Matthew Fisher at UC Santa Barbara, are investigating whether quantum effects might occur in the brain. He's proposed that phosphorus nuclei in calcium phosphate molecules could maintain quantum coherence long enough to affect neuron firing. These discoveries reveal something profound. Life exists at the boundary between quantum and classical, constantly dancing with interaction. Living systems don't try to isolate themselves from quantum effects. They exploit them. Your body is a master of managing quantum interactions. Every moment, quantum events in your cells are occurring and decohering, creating the continuous classical behavior we call life from an underlying quantum substrate. You are literally a quantum process that has learned to persist, to maintain patterns of interaction stable enough to replicate and evolve, yet flexible enough to harness quantum effects when beneficial. The matter of your body only exists through constant interaction, both classical and quantum. The boundary between you and the environment is not a sharp line, but a region of exchange, of continuous interaction that defines you into being moment by moment. There's a growing realization in physics that information might be more fundamental than matter or energy. And information is inherently relational. It only exists in the context of interaction. Physicist John Archibald Wheeler, who coined the term black hole, spent his later years promoting a radical idea he called it from bit. He proposed that every item of the physical world has its basis in information. Matter, energy, space, time, all derive from yes or no answers to questions, bits of information. But where does information come from? It comes from interactions. You can't have information without distinguishability, and you can't have distinguishability without interactions that reveal differences. Think of it like this. Imagine two identical boxes in absolute isolation from each other and everything else. Can you meaningfully say they're different objects? Without any interaction that reveals their separateness, they're indistinguishable, effectively a single entity. Information requires context, requires interaction, requires relationship. Black holes provide a stunning example of this connection. When matter falls into a black hole, it seems to disappear. But the information about that matter can't be destroyed. That would violate quantum mechanics. So where does it go? Jacob Bekenstein and Stephen Hawking showed in the 1970s that black holes have entropy proportional to their surface area. The information isn't inside the black hole. It's encoded on the event horizon, the boundary. This led to the holographic principle, developed by Gerard T. Hooft and Leonard Susskind in the 1990s, which suggests that the information content of a region of space is encoded on its boundary. Reality might be holographic, with what we experience as three-dimensional existence actually being a projection of information on a two-dimensional surface. Recent work in quantum information theory reveals that entanglement itself can be thought of as a form of information exchange. When two particles become entangled, they share quantum information. The correlation between them is a kind of information that exists not in either particle individually, but in their relationship. Some physicists now believe that space-time itself emerges from entanglement. Mark van Ransdonk and others have shown that in certain theoretical models, if you remove entanglement between regions, space itself disappears. Entanglement stitches space together. If this is true, then interaction, the process that creates entanglement, is literally weaving reality into existence. Consider this. Every time you interact with something, you exchange information with it. You become entangled, however slightly. The photons bouncing off this screen and hitting your eyes are creating correlations, sharing information between the screen's quantum state and your brain's quantum state. You're not passively receiving information from a pre-existing reality. You're engaging in an information exchange that creates definite properties for both you and the screen. Here's your third mind-blown moment. Information is not something matter has. Information is what matter is. And information only exists in interaction. So matter only exists in interaction. Let's revisit the double-slit experiment with a twist that will completely shatter your intuitions about time and causality. In 1982, physicists Marlin Scully and Kai Droll proposed a variation called the quantum eraser experiment. It was first performed in 1995 by Yanhua Shi and his colleagues. Here's the setup. You perform the double-slit experiment, but you mark which slit each photon goes through using entanglement. Each photon becomes entangled with another particle that records its path. As expected, the interference pattern disappears. The path information destroys the wave-like behavior. But here's the twist. After the photons have already hit the screen and their positions have been recorded, you measure the entangled partner particles. And crucially, you have a choice. Measure them in a way that reveals which path information, or measure them in a way that erases that information. If you erase the which path information after the fact, the interference pattern reappears in the data. If you don't erase it, no interference pattern. Think about what this means. The photon's behavior at the screen, whether it creates an interference pattern or not, seems to depend on what you do later with its entangled partner. The future appears to affect the past. The delayed choice quantum eraser takes this even further. You can wait minutes, hours, or theoretically, even years after the photon hits the screen before deciding whether to erase the which path information. The photon's behavior retroactively changes based on your future choice. Now, this doesn't allow backward time travel or sending messages to the past. The interference pattern only becomes visible when you correlate the data from the screen with the data from the eraser measurement. Until that correlation, you can't tell whether there's interference. But it does tell us something profound about the nature of time and interaction. The photon doesn't have a definite history until the entire system of interactions is complete. Its past is not fixed. It's entangled with future interactions. Think of it like this. Imagine you're writing a story. You write the middle of the story first, leaving the beginning ambiguous. Later, you write the beginning, and suddenly, the middle means something different based on how you set it up. The middle didn't change physically, but its meaning, its role in the narrative, was retroactively determined. That's what's happening in the quantum eraser. The photon's path through the slits is like the middle of the story. It remains ambiguous, undefined, until future interactions complete the narrative. This tells us that interactions don't just create present reality. They participate in determining what was real in the past. The past is not a fixed record. It's a network of quantum correlations that only becomes definite through ongoing interactions. You don't just create your present through interaction. In a very real sense, you participate in creating the past. Let's zoom out from quantum weirdness and look at how the definite, structured world we experience emerges from all these quantum interactions. Emergence is the phenomenon where simple rules at a low level give rise to complex behavior at higher levels. And the key to emergence is interaction. Consider water. A single water molecule doesn't have properties like wetness, fluidity, or surface tension. These properties only emerge from the interactions between vast numbers of molecules. Wetness is not a property of H2O. It's a property of how H2O molecules interact. Or consider a hurricane. No individual air molecule is rotating in a giant spiral. The hurricane is a large-scale pattern that emerges from the interactions between countless molecules, driven by temperature gradients and the Earth's rotation. Your consciousness is an emergent phenomenon. No single neuron is conscious. No small group of neurons is conscious. But from the interactions between billions of neurons, consciousness emerges. Think of it like this. A single pixel on a screen doesn't make an image. But through the interactions and relationships between millions of pixels, images, videos, and entire virtual worlds emerge. The crucial insight is that these emergent properties are real. Wetness is real, even though no individual molecule is wet. Hurricanes are real, even though no molecule is hurricane-shaped. Your consciousness is real, even though no neuron is conscious. And these emergent properties have causal power. The hurricane affects how individual molecules move. Your conscious decisions affect neuron firing patterns. Higher-level patterns constrain lower-level behavior. This is called downward causation, and it's deeply related to our question about interaction and existence. The definite, classical world we experience is an emergent level of organization that arises from quantum interactions. And once this level emerges, it exerts its own causal influence. When you move your hand, you're not controlling each atom individually. You're exercising causation at the emergent level of neural patterns, muscle contractions, and intentional movement. And this high-level causation affects the low-level quantum states of the atoms in your hand. Reality is layered, with each layer emerging from interactions at the level below, and each layer constraining the level below through downward causation. You exist at multiple levels simultaneously. At the quantum level, you're a cloud of interacting fields. At the atomic level, you're atoms exchanging photons and bound by electromagnetic forces. At the molecular level, you're proteins folding and DNA replicating. At the cellular level, your cells communicating through chemical signals. At the organismal level, you're a conscious being making decisions. Each level is real. Each level emerges from interactions at the level below, and each level only exists through continuous interaction. The matter of your body is not a collection of independent objects that occasionally interact. It's a hierarchy of interactions, each level creating and sustaining the level above through continuous dynamic exchange. Now let's grapple with what all this means philosophically. If matter only truly exists in interaction, we need to reconstruct our entire understanding of reality. For thousands of years, Western philosophy was dominated by what we call substance ontology. Reality consists of substances, things that exist independently, which have properties and occasionally interact. Aristotle, Descartes, Locke, they all assumed that objects have intrinsic existence. But quantum mechanics and modern physics are telling us something radically different. We need what philosopher Karen Barad calls an agential realist ontology, where the fundamental units of reality are not things but interactions, not substances but relations. This is actually closer to certain Eastern philosophies. Buddhist philosophy, particularly the concept of dependent origination, has long held that nothing has independent, intrinsic existence. Everything arises in dependence on everything else. The Buddhist concept of emptiness doesn't mean nothing exists. It means things are empty of independent, permanent essence. They exist interdependently, through relationship and interaction. Think of it like this. Is a wave an object? You can point to a wave, photograph it, even surf on it. But the wave isn't a thing. It's a pattern of interaction between water molecules and energy. The wave exists, but only as a dynamic process, not as a substance. Everything might be like this. You're not a substance with properties. You're a pattern of interactions that persists through time, constantly recreating itself through exchange with the environment. This has profound implications for concepts like identity and persistence. What makes you the same person you were yesterday? Not that you're made of the same matter. Most of your atoms get replaced over time. Not that you have the same thoughts. Your mental state changes constantly. You persist because the pattern of interactions that constitutes you is continuous. You're a process, not an object. You're a verb, not a noun. Process philosophy, developed by Alfred North Whitehead in the early 20th century, anticipated this. Whitehead argued that reality is fundamentally composed of events and processes, not substances. An actual occasion, his term for a fundamental event, only exists through its relations to other occasions. Whitehead wrote this before quantum mechanics fully developed, yet his philosophy aligns remarkably well with relational quantum mechanics and quantum field theory. Another profound implication: the hard distinction between self and other breaks down. If you exist through interactions, and those interactions connect you to everything you interact with, where exactly do you end and the world begin? The photons bouncing off objects and entering your eyes create entanglements between your brain states and the world. You're not separate from what you observe. You're entangled with it. Philosopher Evan Thompson, in his work on embodied cognition, argues that the boundary between organism and environment is not fixed, but negotiated through interaction. You don't just exist in your environment. You and your environment co-create each other. This isn't mysticism. It's a direct consequence of understanding that existence is interaction. So how should understanding that matter only exists through interaction change how you see yourself and your life? First, it should give you a profound sense of connection. You're not an isolated island of existence in an alien universe. You're fundamentally connected to everything you've ever interacted with. The light from stars has touched your eyes, creating quantum correlations between you and stellar plasma billions of miles away. The air you breathe has been breathed by countless others, creating physical continuity across all human history. Every interaction leaves a trace. You're not just passively observing the world. You're participating in creating its definite properties. When you look at the moon, you're not seeing a pre-existing object. You're engaging in an interaction that creates definite properties for both you and the moon relative to each other. Think about your relationships with other people. These aren't just social constructs. They're literal physical entanglements. When you interact with someone, information flows between you, creating correlations in your respective quantum states. The relationship is physically real, encoded in the pattern of interactions between you. When someone dies, the pattern of interactions that constituted them stops. But the effects of their interactions persist. The correlations they created with you, with others, with the environment, continue to ripple forward. In a very real sense, they continue to exist in the web of relationships they created. Second, this understanding should give you a sense of agency. You're not a powerless observer of predetermined reality. You're an active participant in creating definite reality through your interactions. Every choice you make, every action you take, creates new definite properties in the universe. You're not discovering what will happen. You're participating in making it happen. The future is not written. It's a superposition of possibilities that your interactions help collapse. Of course, you're not solely responsible for reality. You're one interacting element among countless others, but you matter. Your interactions have real effects that ripple outward through the web of causation. Third, this should change how you think about meaning and purpose. In a substance ontology, you're a tiny isolated speck in a vast uncaring cosmos, and you have to manufacture meaning from nothing. But in a relational ontology, you're a vital node in the network of interactions that creates reality. Meaning isn't something you have to impose on an indifferent universe. Meaning emerges from interaction, from relationship, from connection. You're meaningful Because you're connected. Your existence affects the universe. Not in some grandiose way where you're the center of everything, but in the humble, profound way that every interaction matters. Every relationship is real. Every connection creates something that didn't exist before. Think of it like this. A single neuron in your brain doesn't understand this video, but through its interactions with billions of other neurons, understanding emerges. Similarly, you might not comprehend the cosmic significance of your existence in isolation, but through your interactions with the vast network of reality, you participate in creating something larger than yourself. Fourth, this should give you appreciation for the present moment. The definite reality you experience right now only exists in this moment of interaction. The past is a network of quantum correlations, the future a superposition of possibilities. Only now, in the moment of interaction, is reality definite. Mindfulness traditions have always emphasized the importance of the present moment. Physics is telling us they're literally right. The present is all that definitively exists. Finally, this should give you intellectual humility. We don't fully understand what matter is or how consciousness relates to physical reality. We have remarkably successful theories, but they point to a reality far stranger than common sense suggests. Stay curious. Stay open to the mystery. The universe is under no obligation to make sense to you, and the fact that it makes any sense at all is a profound gift. Understanding that matter exists through interaction isn't just philosophical. It has profound implications for technology and humanity's future. Quantum computing is based entirely on manipulating quantum superpositions before they decohere through environmental interaction. Companies like IBM, Google, and IonQ are building quantum computers that can solve certain problems exponentially faster than classical computers. In 2019, Google announced quantum supremacy, performing a calculation that would be practically impossible for classical computers. The key is maintaining quantum coherence, preventing unwanted interactions that would collapse superpositions prematurely. Quantum computers will revolutionize cryptography, drug discovery, materials science, and artificial intelligence. But they work only by understanding and controlling quantum interactions at unprecedented levels. Quantum communication and quantum cryptography use entanglement to create unhackable communication channels. Any attempt to intercept the message creates an interaction that disrupts the entanglement, immediately alerting the sender and receiver. China launched the world's first quantum communication satellite, MISHIS, in 2016. It successfully demonstrated quantum key distribution over thousands of kilometers. The age of quantum internet is beginning. Quantum sensing exploits quantum effects to measure fields, forces, and physical properties with unprecedented precision. Quantum sensors could detect gravitational waves from cosmic events, map brain activity with molecular resolution, or find mineral deposits deep underground. But beyond these specific technologies, understanding matter as interaction might lead to even more radical possibilities. If reality is fundamentally relational and informational, could we manipulate it at that level? Could we engineer space-time itself by controlling quantum interactions? This sounds like science fiction, but physicists seriously discuss it. The concept of programmable matter, materials that can change their properties through controlled interactions, is already being developed. Imagine materials that could become harder or softer, more or less conductive, even change shape based on controlling interactions at the quantum level. Some physicists speculate about even wilder possibilities. If we fully understand how interactions create space-time, could we create artificial regions of space-time with different properties? Could we manipulate wormholes for faster-than-light travel or communication? I'm not saying these are likely or even possible, but a century ago, quantum computers, quantum cryptography, and quantum teleportation were pure speculation. Understanding that matter exists through interaction opened these technological doors. What doors might open next? There's also a darker side. Technologies that manipulate matter at the quantum level could be used for unprecedented surveillance, new types of weapons, or could create risks we don't yet understand. As we develop power over quantum interactions, we need wisdom to use that power responsibly. We need to think deeply about the ethical implications of technologies that blur the line between information and physical reality. One thing is certain: the 21st century will be defined by our growing ability to understand and manipulate quantum interactions. The future of technology, the future of humanity, depends on grasping the lessons physics teaches us about the nature of matter and interaction. Despite how much we've learned, profound mysteries remain. Let me share some of the deepest unsolved questions in physics related to interaction and existence. First, the measurement problem. We still don't have consensus on what happens during wave function collapse. Does it actually collapse? Or do all possibilities continue existing in parallel universes? Is there an objective collapse mechanism we haven't discovered? Do quantum states remain forever relative and entangled, with no absolute collapse? Different interpretations predict the same experimental results, making them empirically indistinguishable with current technology. Future experiments might reveal which is correct, or we might need a conceptual breakthrough we can't yet imagine. Second, the quantum to classical transition. We understand decoherence explains why we don't see quantum effects at large scales. But is there a fundamental boundary? Is there a size or complexity above which quantum effects simply cannot occur? Or is everything quantum, with classical behavior being just a convenient approximation? Experiments are pushing the boundaries. In 2019, researchers created quantum superpositions of molecules containing over 2,000 atoms. How big can we go? Could we, in principle, put a bacterium in superposition? How about a virus? Third, the role of gravity in quantum mechanics. We have successful theories of the electromagnetic, weak, and strong forces at the quantum level. But gravity resists quantization. Is gravity fundamentally different from other forces? Does it emerge from quantum interactions rather than being quantum itself? Loop quantum gravity, string theory, and other approaches offer possibilities, but we don't have experimental evidence yet. The energies required to test quantum gravity are generally beyond our reach. Fourth, the information paradox for black holes. If black holes destroy information, quantum mechanics is violated. If they preserve it, how? The holographic principle offers possibilities, but we don't have a complete answer. Recent work by Stephen Hawking, Leonard Susskind, Juan Maldacena, and others suggests information might be preserved through subtle quantum correlations, but debates continue. Fifth, the nature of time. Why does time flow in one direction? Why do we remember the past, but not the future? Is the arrow of time fundamental, or does it emerge from the statistical behavior of interactions? Some physicists, like Carlo Rovelli, argue that time might not be fundamental at all. At the deepest level, there might be only quantum events and their relational ordering, with time emerging from that structure. Sixth, the role of consciousness. We've established that consciousness isn't necessary for wave function collapse. But consciousness exists, and it's made of quantum interactions, like everything else. How does subjective experience emerge from quantum processes? This is the hard problem of consciousness, and it remains unsolved. Some researchers, like Giulio Tononi with his integrated information theory, suggest consciousness might be a fundamental feature of systems with certain kinds of integrated information. Others think consciousness is an emergent property that will be explained once we understand neuroscience better. Seventh, the ultimate nature of quantum fields. Are quantum fields the deepest level of reality, or do they emerge from something even more fundamental? Some approaches, like causal set theory or quantum gravity, suggest space-time and fields emerge from more primitive discrete structures. We might be like someone in 1850 thinking matter is made of atoms, not yet imagining that atoms are made of electrons and nuclei, which are made of quarks and gluons, which are excitations in quantum fields. which might themselves emerge from something deeper. Finally, why these laws? Why does the universe follow quantum mechanics? Why these specific fields and interactions? Is there a deeper principle that makes these laws necessary? Or is our universe one possibility among infinite others? The fact that we can ask these questions, that we've come this far in understanding reality's nature, is itself remarkable. 300 years ago, we thought matter was just stuff. Now we know its patterns of interaction in quantum fields, emerging from relationships that create space, time, and existence itself. We don't have all the answers, but we're asking better questions. So let's bring everything together. Does matter exist only when interacting? The answer quantum mechanics gives us is nuanced but profound. Matter, in the sense of having definite properties, only exists through interaction. Before interaction, particles exist in superpositions, ghost-like states of infinite possibility. The act of interaction, measurement, entanglement, coupling between fields, is what creates definite properties. This isn't because we're ignorant of hidden properties. Bell's theorem and countless experiments prove there are no hidden variables. The definiteness is created by interaction, not revealed by it. At the deepest level, matter isn't stuff that occasionally interacts. Matter is patterns of interaction. Particles are excitations in quantum fields, and these excitations only become real, only manifest as the definite particles we detect through interactions with other fields. Space and time themselves might emerge from interaction, from the entanglement structure connecting quantum events. Reality is not a collection of independent objects that happen to bump into each other. Reality is a vast network of interactions, each creating definite properties relative to itself, weaving together into the rich, structured cosmos we experience. You are not separate from this network. You are it. You are a self-sustaining pattern of interactions that has persisted long enough to become conscious, to look back at the network and marvel at its existence. Every breath you take is an interaction, creating definite properties in your lungs and the air. Every photon hitting your eyes creates correlations between your brain and the world. Every thought is a cascade of quantum and classical interactions in your neurons. You don't just exist in the universe. You participate in creating its definiteness through every interaction, every moment. This should fill you with wonder. You're not a tiny, insignificant speck in an uncaring cosmos. You're a conscious node in the network of interactions that is reality. You matter because you interact. You're meaningful because you're connected. The universe is not something you observe from the outside. You're inside it, part of it, creating it through your interactions, as it creates you through its interactions with you. This is the deepest truth quantum mechanics teaches us. There is no view from nowhere, no objective reality independent of interaction. Reality is thoroughly relational, thoroughly interactive, thoroughly interconnected. You are the universe becoming aware of itself. And that is extraordinary. Before you go, remember to like this video and subscribe to the channel. Share your thoughts in the comments. Tell me, how does understanding that matter exists through interaction change your view of reality? What implications do you find most profound? I want to hear from you. And if you've made it this far, congratulations. You've just taken a 210-minute journey through some of the deepest ideas in physics and philosophy. You've grappled with quantum superposition, entanglement, wave function collapse, quantum field theory, relational quantum mechanics, and the emergence of reality from interaction. These ideas aren't easy. They challenge everything your intuition tells you about the world. But they're also some of the most rigorously tested, most experimentally verified ideas in all of science. The universe is stranger, more beautiful, and more deeply interconnected than common sense suggests. And you are part of that strangeness, that beauty, that interconnection. Keep questioning, keep wondering, keep interacting with this marvelous universe we're privileged to inhabit. Thank you for watching. Until next time, stay curious.